Sigma phase embrittlement damage mechanism is a part of mechanical and metallurgical failure mechanisms. Description of sigma phase embrittlement based on API 571. Formation of a metallurgical phase known as sigma phase can result in a loss of fracture toughness in some stainless steels as a result of high temperature exposure. Sigma phase embrittlement is a phenomenon primarily affecting certain stainless steels and other alloyed materials, particularly those with significant chromium content, when exposed to elevated temperatures, typically between 600 degrees Celsius and 1000 degrees Celsius or approximately 1112 degrees Fahrenheit to 1832 degrees Fahrenheit. In general, description of sigma phase embrittlement damage mechanisms are as following but not limited to. Number 1 is phase formation. Sigma phase is a brittle intermetallic compound, or FeCr, often noted as FeCr, that forms during prolonged exposure to high temperatures in specific alloy compositions. Its formation is typically associated with the precipitation of the sigma phase from the solid solution of the steel matrix. Number 2 is microstructural changes. The presence of the sigma phase leads to significant microstructural changes within the material. Distinct grain boundaries become compromised as the sigma phase precipitates, resulting in the formation of a hard, brittle microstructure. The balance between ferrite and austenite phases is disrupted, further contributing to embrittlement. Number 3 is mechanical properties. As sigma phase forms, the mechanical properties of the alloy degrade. The material becomes less ductile and more brittle, which severely reduces its toughness. This embrittlement can lead to the initiation of cracks under stress, which compromises the integrity and reliability of components in service. Number 4 is service impact. Components affected by sigma phase embrittlement may experience premature failure under thermal or mechanical loads. This is particularly critical in applications where materials are subject to cyclic loading or thermal cycling, such as in power plants, petrochemical facilities, and high-temperature furnaces. Number 5 is preventive measures. To mitigate sigma phase embrittlement, alloy design strategies include maintaining a balanced composition and limiting the exposure time at elevated temperatures where sigma phase can form. Heat treatment processes may also be implemented to dissolve the sigma phase and restore ductility. Overall, understanding sigma phase embrittlement is crucial for materials engineers and metallurgists to ensure the long-term performance and safety of high-temperature applications involving alloy materials. Affected materials. Sigma phase embrittlement is a degradation mechanism primarily associated with certain stainless steels and high-temperature alloys, particularly in environments with high temperatures and the presence of elements like chromium and molybdenum. The main materials affected by sigma phase embrittlement include. Number 1 is austenitic stainless steels, grades such as 304, 316, and others that contain high levels of chromium and nickel can be susceptible to sigma phase formation. Number 2 is ferritic stainless steels. Some ferritic stainless steels may also be affected, particularly those with higher chromium content. Number 3 is superalloys. High-performance alloys used in aerospace, chemical processing, and power generation, such as Inconel and certain nickel-based superalloys, can experience this type of embrittlement. Number 4 is heat-resistant alloys. Alloys designed for high-temperature applications can also be prone to sigma phase embrittlement if they have a suitable composition and are subjected to prolonged exposure at elevated temperatures. Number 5 is martensitic stainless steels. Certain martensitic grades may exhibit sigma phase embrittlement under specific conditions, particularly when subjected to high temperatures. In general, sigma phase embrittlement is more likely to occur when the material is exposed to temperatures typically between 600 degrees Celsius and 1000 degrees Celsius, or 1112 degrees Fahrenheit to 1832 degrees Fahrenheit, for extended periods. The sigma phase is a brittle intermetallic compound that forms in certain alloy compositions, leading to a loss of ductility and mechanical integrity. This phenomenon can significantly affect the performance and reliability of components made from these materials in high-temperature applications. Sigma phase embrittlement is a degradation mechanism that affects certain types of stainless steels, particularly those containing significant amounts of chromium and molybdenum. This phenomenon is particularly prevalent in high-temperature applications and can lead to serious failures in components. The critical factors that contribute to sigma phase embrittlement include: Number 1 is alloy composition. The presence of chromium, molybdenum, and sometimes tungsten can promote the formation of sigma phase. Steels with a higher concentration of these elements are more susceptible. Number 2 is temperature. Sigma phase forms more readily at elevated temperatures, typically between 600 degrees Celsius and 900 degrees Celsius, or 1112 degrees Fahrenheit and 1652 degrees Fahrenheit. Prolonged exposure to these temperatures can accelerate its formation. Number 3 is time of exposure. The duration of exposure at critical temperatures is crucial. Extended time at elevated temperatures allows for more sigma phase to form, leading to embrittlement. Number 4 is cooling rate. Rapid cooling can sometimes inhibit the formation of sigma phase, while slower cooling rates after high-temperature exposure can allow for its precipitation. Number 5 is microstructural factors. The initial microstructure of the steel, such as grain size, phase distribution, can impact susceptibility. Fine-grained microstructures might be less prone to embrittlement compared to coarse-grained structures. Number 6 is stress conditions. Applied stresses, both tensile and residual stresses, can influence the embrittling effects. Parts that are under high stress may fail more readily when sigma phase is present. Number 7 is pressure and environment. The operating environment can also play a role, particularly in the presence of corrosive media that might exacerbate embrittlement and crack propagation. Number 8 is presence of other phases. The presence of other microstructural constituents, like carbides, nitrides, or other secondary phases, can interact with sigma phase and influence its embrittling effects. Number 9 is thermal cycling. Repeated thermal cycling can also lead to the formation and/or dissolution of sigma phase, thus affecting the material's properties over time. Understanding these critical factors is essential for predicting sigma phase embrittlement and implementing mitigation strategies in materials design and processing, particularly for high-performance applications in industries like aerospace, petrochemical, and power generation. Affected units or equipment. Sigma phase embrittlement is a phenomenon that occurs primarily in certain high-temperature nickel-based and stainless steels, particularly those that contain a significant amount of chromium. It is most commonly observed in austenitic stainless steels and some superalloys used in high-temperature applications. The affected units or equipment typically include: Number 1 is piping systems. High-temperature piping systems in power plants, chemical plants, and industrial processes can be susceptible to sigma phase embrittlement, especially in areas where temperatures fluctuate. Number 2 is heat exchangers. Components subjected to high temperatures over prolonged periods can experience embrittlement, leading to cracking or failure. Number 3 is pressure vessels. Equipment designed to hold gases or liquids at high pressures may be compromised, particularly if they utilize austenitic stainless steels. Number 4 is turbine components. Elements within gas and steam turbines that operate at high temperatures may be affected, compromising their structural integrity. Number 5 is furnaces and reactors. Components within high-temperature reactors and furnace systems, particularly those with prolonged exposure to heat, can be susceptible. Number 6 is welds and weld HAZ, or heat-affected zones. Areas where welding has occurred may be more prone to sigma phase formation and embrittlement due to the thermal cycles involved. Number 7 is high-temperature components. Any components that undergo long-term exposure to high temperatures, especially those in the aerospace, nuclear, and petrochemical industries. Overall, the presence of sigma phase embrittlement can significantly degrade the mechanical properties of affected materials, leading to increased susceptibility to cracking, loss of ductility, and ultimately structural failure. It is crucial to monitor temperature conditions and manage alloy compositions carefully to prevent this type of embrittlement in susceptible materials. Appearance or morphology of damage. Sigma phase embrittlement is a phenomenon that occurs primarily in certain stainless steels and nickel-based alloys when exposed to high temperatures, typically in the range of about 600 to 1000 degrees Celsius, or 1112 to 1832 degrees Fahrenheit. The appearance or morphology associated with sigma phase embrittlement can be characterized by several key features. Number 1 is microstructural changes. The most significant aspect of sigma phase embrittlement is the formation of the sigma phase, which is a brittle intermetallic compound. This phase is typically identified as a distinct, often darker phase in micrographs and can appear as needles or platelets within the matrix of the alloy. Number 2 is intergranular fractures. The presence of sigma phase can lead to brittle intergranular fracture paths, which are evident in fracture surfaces. Instead of ductile tearing, you may see flat, shiny surfaces and a lack of necking, indicating a failure mode that is more typical of brittle materials. Number 3 is reduction in ductility. Structures that have undergone sigma phase embrittlement often exhibit visibly reduced ductility. This can manifest as cracking or failure with little to no deformation beforehand. Number 4 is changes in hardness. The formation of sigma phase can lead to localized increases in hardness, as this phase is significantly harder than the primary matrix phase. Hardness testing might show anomalously high values in areas containing sigma phase. Number 5 is increased porosity or localized weakness. In some cases, you may observe localized areas that appear more porous or weaker, as the sigma phase can segregate along grain boundaries and disrupt the overall coherence of the microstructure. Number 6 is color changes. In certain cases, thermal exposure before sigma phase formation may cause oxidation or discoloration of the surface of the alloy, leading to visual changes that may precede or accompany the embrittlement. Overall, the appearance of sigma phase embrittlement usually involves distinct microstructural features that can be observed through metallurgical techniques such as optical microscopy or scanning electron microscopy, SEM, alongside a clear indication of the material's mechanical properties degrading. Prevention and/or mitigation. Sigma phase embrittlement is a type of corrosion-related failure that affects certain high-temperature alloys and steels, particularly those containing chromium, molybdenum, and tungsten. It's essential to prevent or mitigate this type of damage to ensure the structural integrity and lifespan of critical components. There are numerous prevention strategies could be considered to use in case of sigma phase embrittlement. The first is material selection. Choose materials resistant to sigma phase embrittlement, such as low alloy steel, or select alloys with compositions that avoid the formation of sigma phase precipitates. The second is thermal treatment. Implement thermal treatments, like stress relief annealing or solution heat treatment, to minimize sigma phase formation during manufacturing. The third is mechanical treatment. Apply mechanical stress to reduce or eliminate sigma phase precipitates. For example, cold working can help to refine grain size. The fourth is coatings or surface treatments. Apply protective coatings or surface treatments, such as ceramic or plasma-sprayed coatings, to isolate the alloy from corrosive environments. The fifth is welding and joining. Employ proper welding and joining techniques to avoid introducing defects or stress concentrators that can facilitate sigma phase precipitation. There are numerous mitigation strategies could be considered to use in case of sigma phase embrittlement. The first is monitoring and inspection. Regularly inspect components for signs of sigma phase embrittlement, such as microcracking, surface cracks, or intergranular corrosion. The second is corrosion control. Implement effective corrosion control measures, including maintaining a clean and dry environment, preventing water ingress, and ensuring a stable pH level. The third is heat treatment. Perform heat treatment to restore the microstructure of affected components and remove sigma phase precipitates. The fourth is material replacement. Replace severely damaged or degraded components with new, sigma phase embrittlement resistant alloys. The fifth is design optimization. Redesign components to reduce stress concentrations and promote uniform stress distribution, which can help mitigate sigma phase embrittlement. Additional considerations in case of prevention and/or mitigation strategies for sigma phase embrittlement damage mechanisms. The first is consult with materials experts and engineers to ensure the proper selection of materials and implementation of prevention and mitigation strategies. The second is continuously monitor the performance of critical components and implement corrective actions as necessary. The third is develop and maintain comprehensive maintenance and inspection schedules to detect potential issues before they become critical. Preventing and mitigating sigma phase embrittlement requires a proactive, multifaceted approach that combines material selection, thermal treatment, mechanical treatment, coatings, and regular inspections. By adopting these strategies, you can minimize the risk of sigma phase embrittlement and ensure the long-term performance and safety of critical components. Inspection and monitoring. Sigma phase embrittlement is a form of degradation that can occur in high-temperature stainless steels, particularly in the 300 series, such as 304, 316, when exposed to prolonged service at temperatures between approximately 600 degrees Fahrenheit to 1300 degrees Fahrenheit or 316 degrees Celsius to 704 degrees Celsius. The sigma phase is a brittle intermetallic compound which can adversely affect the mechanical properties of the steel, making it more susceptible to cracking and failure. To detect sigma phase embrittlement and assess the integrity of materials, various inspection and monitoring methods can be used. Number 1 is metallography. It is commonly divided by 3 but not limited to the following. The first is optical microscopy. Thin sections of the material can be polished and etched to reveal microstructural features. Sigma phase appears as a distinct phase with a characteristic appearance, which can be identified through optical microscopy. The second is scanning electron microscopy, or SEM. SEM can provide high-resolution images that help identify the presence of sigma phase and its distribution within the microstructure. The third is transmission electron microscopy, or TEM. TEM can be used for more detailed analysis at the atomic level, allowing for the precise identification of phases present in the material. Number 2 is X-ray diffraction, or XRD. X-ray diffraction, or XRD, can be employed to identify the presence of the sigma phase by analyzing the diffraction patterns generated when X-rays interact with the crystalline structure of the material. Number 3 is energy dispersive X-ray spectroscopy, or EDS. Often used in conjunction with scanning electron microscopy, or SEM, energy dispersive X-ray spectroscopy, or EDS, can provide elemental composition analysis to confirm the presence of the sigma phase and understand its formation. Number 4 is mechanical testing. The first of mechanical testing which commonly used is tensile testing. The mechanical properties of affected materials can be evaluated through standard tensile tests to observe reductions in yield strength and ductility. The second of mechanical testing which commonly used is Charpy-Vienach impact testing. This can be used to assess the toughness of materials, as sigma phase embrittlement typically leads to decreased impact resistance. Number 5 is hardness testing. Increased hardness may be indicative of sigma phase formation. Standard hardness tests, such as Rockwell, Vickers, can help assess changes in hardness that suggest embrittlement. Number 6 is ultrasonic testing. Ultrasonic methods can help detect microcracking and changes to material integrity by analyzing the propagation of sound waves through the material. Number 7 is eddy current testing. This non-destructive testing method can help identify changes in electromagnetic properties associated with different phases or microstructural changes. Number 8 is thermal analysis. Techniques such as differential scanning calorimetry, or DSC, can help identify phase transitions and changes in material properties as a result of heat treatment or prolonged exposure to elevated temperatures. Number 9 is service condition monitoring. Monitoring operating conditions, temperatures and times, can help predict the risk of sigma phase formation, allowing preventive measures to be put in place before significant damage occurs. Using a combination of these methods allows for a comprehensive assessment of potential sigma phase embrittlement in high-temperature applications. Regular monitoring, especially in components subjected to prolonged service at elevated temperatures, can assist in mitigating the risk of catastrophic failure due to sigma phase formation. Thank you.